You're good.
I think everyone's going to calculus.
I'm not going to calculus.
Johannes, are you?
I'm going to try.
You are?
Okay, Janan, Nikki, me, Alba, are you?
Uh-huh.
Or four-way. Four, high five.
You are?
5. Yes, you are. Janan has your choice.
Yeah.
I'll hunt her down and beat
Janan,
her.
You shut.
Okay, stop. All right, now.
Hey! Okay.
Okay. Instantaneous rates. All right, here's what we have to start with. Okay. Johannes? Okay, all right.
Paper.
We'll actually pause a moment for
Wait,
him.
isn't instant technically...
Not
I
me.
already picked it. All right, Alba, start recording it.
I'll
Okay,
get started.
now, Ramsey, come on up here for a second.
Should he cover his face?
Probably in a minute.
A blur.
No, he's fine. He's okay. All right, can you see Ramsey and I?
Yeah.
Okay.
I
right.
probably look so mysterious.
Now, here's what I'm going to do, guys, okay? I am going to move my right hand approximately 30 inches in 6 seconds. And I'm going to do
you want me
so
to stand
twice. That's fine. That should be
Okay.
okay. And you guys, we're going to just spend the entire rest of the class quickly discussing the differences between the two motions. Are you ready? Okay. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi. Move my hand about 30 inches in about 6 seconds. Now I'm going to do it again. Okay? 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi.
It doesn't look the same from the side.
Probably doesn't. That was a lame sound
From the
too. It
back
really
it
should have been
does.
a little bit more like that. But, all right, no, you didn't flinch that time. I am impressed. Okay, Ramsey, thank you. Have a seat. All right, now.
Oh, I'm up here.
Don't make me happy. All right, now. First punch. Let's analyze these graphically first. The first punch. We moved. I only need quadrant 1. I'm going to do a little bit of very simple mathematical modeling here. I'm going to do that part very quickly. So try to follow along and ask questions, and hopefully I'll have time to answer them. I only need quadrant 1. There was nothing I would describe as negative motion or negative time in that. I started at 0 seconds, having moved 0 inches. I moved 30 inches of distance over 6 seconds of time. Okay? I wound up here. Obviously, almost no human motion is perfect, but still, I think this is a pretty good
Only mine.
approximation of what happened. So at 1 second, about how far had I moved?
30 divided by 6.
5.
5 inches.
Thank you, guys.
Okay. What's the slope of this line?
5.
Yes. The slope is the dependent variable divided by the independent
5 up,
variable.
1 over.
Distance by time. So it's 5 inches per every 1 second. Okay? Any questions on the first punch? Is that about what happened? And then it stopped?
Wait, is that M for slope?
And M is for slope, yes.
Wait, the first punch you just went like this.
Steady,
because
very
I could
slow and
really-
steady.
But did you hit him?
No, it didn't actually hit him, no.
But
I mean, it did go, yes. Yes, it went right by his chin. Good question. Here at 4 seconds. And at that point, I had moved about 20 inches. Okay, so this was actually the point of contact, had I been actually punching one of my students in the face. The second punch will require a more complicated mathematical model. And mathematical modeling can be fun, but this exercise is going to be, see how well you guys can follow along and you take something that actually happened and try and figure out, describe it mathematically. Was my hand moving steadily
Yes.
in the second punch?
No.
Over the whole 30-second
Oh
interval?
no, you didn't punch until like 6 seconds.
So 4 seconds.
4.
Yeah, Ramsey was paying close attention.
I was getting punched.
That's right.
When I...
It does tend to focus the mind nicely. So what happened was, I've timed myself a little bit on this. At 4 seconds, my hand started to move. I probably finished it in about 1/10 of a second. Very approximate here. So at 4 seconds, I'm here on the graph, and 1/10 of a second later, my point of contact is about here at 4.1, comma 30. 4.1 seconds, 30 inches, we have a hit. In between 0 seconds and 4 seconds, how much did my fist move?
None.
None. After 4.1 seconds, how much did my fist move?
30 inches.
Well, it was at 30 inches,
Did
but
it
it didn't move.
stay?
It stayed still at a
At
point.
30 inches.
At a point 30
Right,
inches from
yeah.
where it started. It stayed still there, and here, I should thicken this a little bit, because at this 0 inches, this was my fist not moving at all. In between, with a punch, you don't try and throw a punch at a constant speed, you try to
Why
accelerate.
is it 4.1? Because it was like right after 4.
Yeah, it took me about a tenth of a second to do that. Probably a little less, but on a good
I
day.
didn't flinch.
But he did not
Throw
flinch.
that out there.
Now, this drawing's not going to be hugely helpful, but it's not a straight line. Don't try to draw this yet. We'll talk about this in a minute. When you're throwing a punch, you're trying to accelerate as much as possible. Technically, you're decelerating a little bit at the end of the punch, but that was when I was past his face, so that's less important. So you're really, really trying to accelerate. And if you're successfully accelerating, a good model for acceleration is a parabola. It's not perfect, but a quadratic model always represents acceleration, like we did with gravity and physics. Okay? So I'm going to make the assumption that there's a parabola that can describe my fist acceleration from here to here. Okay, that's my first assumption. After that, everything will be, no more assumptions, it will all be
Wait,
true.
is that dotted line coming out of 4.1?
This was just to help me draw it.
No, I mean the
Oh, this one?
Yeah.
This was just to help me line it up.
Oh,
Yeah, it wasn't, that's not part of the graph.
then why is it coming out of 4?
It's
is that-
supposed to be coming out of 4.1, the dotted one, and the solid one is supposed to be coming out of, oh, this bit.
So there should be a solid line right there.
No, it's not a line, it's actually the world's skinniest parabola. From 4 seconds here up to 4.130
Oh,
should
it's
be the
going like
world's
that?
skinniest parabola. That's me trying to
it's going
accelerate
like
my
that.
fist.
Oh, okay.
That's my fist going from 0.
Got it.
It's half a parabola, right?
Yeah, just half. Yes, just half the
And
parabola.
the A is 0.1.
Hold that thought. You're on this step. Okay. Fastest way to model something with a parabola. And Janan's already started. For the punch itself,
Which punch?
the second one. For the
Which
second
punch?
punch while you're actually punching it, not that first slow one. Okay?
I was on fire.
What we're going to
So
do,
was-
since we're going to use a parabola as a model, I'm going to go to vertex form of a parabola. Okay? Where's my vertex? If this is the, as Nick pointed out, if this is just the right half of a parabola.
It's not the point 4.1.
3.9.
Close. So I started moving right at 4 if I timed it right. So where's the vertex of this parabola going to be?
0, 4.
Oh.
4,
Oh,
0.
yeah,
Exactly
yeah.
wrong. So the
Oh.
vertex should be at 4, 0. Okay? Now we're going to test Janan's idea here about what the A should be. Because remember, A only works if it's over 1. You have to go over 1 to see how high up A goes. So I think A is going to be a little bigger. Here's a trick you may have done in Algebra 2. We haven't, I don't think, reviewed it this year. So now we're looking at the parabola y equals A times x minus 4 squared plus 0.
So it's going to be 0.1.
No, because remember that A value, that using it that way, only works if you go over 1 unit on the x-axis. That's how fast you go up. But at 5 seconds, I'd stop my fist and the parabola no longer counts.
So A is your slope. You have
Kinda
to
like slope.
divide 0.1 by crap.
Well, there's a simpler trick to this, okay? So the parabola is y equals something times x minus 4 squared, right? Here's what we have to find A. We have another x and y point on the parabola.
So we plug in
X for x, y for y. You may have done that in Algebra 2. Maybe not. I think I taught this 1 year in Algebra 2 this way. But I'm going to plug in 30 inches for y and 4.1 seconds for x, and I'm going to solve for the A value that must occur on that parabola. Given any 3 points, you can find a parabola. Given 2 points, if one's the vertex, you can find the equation this way. So 30 equals A times 0.1 squared.
A equals 3,000.
Yep. 0.1 is 1/10, square it, get 100, multiply both sides. A is going to be 3,000. So my parabola that models
what?
my 30 equals A times 0.1 squared. 0.1 squared, I think of it as 1 over 10. So that's A times 1 over 10
Okay.
squared, or A over 100. Multiply both sides by 100. You'll get A equals 3,000. So my punch can be modeled, I think,
It yields.
from the beginning of my punch to the first 1/10 of a second. I think y equals 3,000 times x minus 4 squared will give me a pretty good approximation of me trying to accelerate my punch. Okay? How fast, here's the question. At the exact instant of contact, if I'd actually hit Ramsey in the chin, how fast would my
You
fist be
should've.
moving?
We need the formula for instantaneous velocity.
I feel like we're in physics class.
This is a bit of a physics lesson. But I always start calculus this way. So we're going to do it mathematically, though. We're not going to measure it. But I'm curious, if that model is accurate, I should be able to use that model to figure out how fast my fist was going when it would have hit Ramsey's jaw. If it's not accurate, this is all pointless. I'm only going to erase the first punch. And I'm going to do a little bit more over here. Okay. Physics. I'm glad I shouldn't have to review that with anyone in the room right now.
Because Megan's not here.
It's not here. Average speed.
So sorry,
D2 minus D1 over T2 minus T1. Look familiar?
Yes.
Yep.
You should look very familiar.
It's velocity.
It's the velocity. If you know the direction, it's velocity. If you don't, it's just speed. We're not really going to worry about direction right now. Average speed is pretty easy to find. Think about the first punch for a second. You guys already found the average speed of the first punch. You found the average speed when you found the slope. Yes. So for the first punch,
It's just 5.
yeah, the average speed equaled the slope, which was 30 minus 0 over over 6 minus 0. 30 minus 0, 6 minus 0, and it was 5 inches per second. So that was pretty simple. Okay? Think this one's going to be as simple?
What, Mr. Belmo?
Yeah.
I could go 5 inches per second. So let's say this is 5 inches.
Yes.
Then there's a difference between me going 1 Mississippi and 1 Mississippi. You
Yes.
know what I mean?
Bingo. There's a lot of differences.
So what's the difference mathematically?
Useful explanation.
We're about to get there. Okay. First off, on the second punch, on this, technically, and this is a stupid way to look at this, I'll admit, but technically what's going on this graph is there's 6 seconds of time and 30 inches of motion, right? But do you think that fast punch really would have hit Ramsey at only 5 inches per second? No. So the average time from here to the end is useless on this one. Doesn't tell us anything. We need to shrink the interval. First off, do the times when my fists aren't moving, are they interesting to us at all? No, not at all. So we can kind of forget about 2 parts of the function. Oh, I forgot to do one thing. I'll come over here and do this. However, since we're talking about the whole 6-second interval, here's how we would talk about it. I would model this, and there's some choice to this, to say P of x, the punch over the 6 seconds, equals piecewise bracket, it's going to have 3 things on it, equals 0 from 0 seconds up to 4 seconds, but not including 4 seconds, equaled 3,000 x minus 4 squared from 4 seconds to 4.1 seconds, and then my fist just sat there 30 inches from where it started from 4.1 until 6. So this graph here would have to be graphed by a piecewise function. A horizontal line at 0, a parabola while I'm trying to accelerate my fist, and a horizontal line at 30 inches. That would graph what I did over those 6 seconds. But getting back to my original question, for terms of how fast I hit Ramsey, are these 2 of any use?
No.
No, so for this particular problem, we can forget about it.
Why did you write all this then?
Oh, just wanted to give, because we need to review piecewise functions a little bit for some of the other things we're doing. I just wanted to make sure you knew how to model that whole situation. But we're only going to care about this one now mathematically. Okay.
It gets really blurry when I zoom in.
Oh, that's because it's a digital zoom. It's not a lens zoom. All it's doing is reducing the resolution. So you might as well leave it all the way out, and then if they want to zoom in, they can do it on the computer screen later.
For the users at home.
That's right. Okay, now, looking at this. Janan, you were the one pointing out the problems with average speed a second ago. What interval does it start making more sense? Over what interval does it start making more sense to measure average speed in this situation?
4 to 6.
Really? 4 all the way to 6? I was done by 4.1.
Oh, well, yeah, 4.
0 to
Yeah.
4.1.
0 to 4.1, I didn't start to 4.
4 to 4.1.
4 to 4.1. It's ridiculous. It's just this tiny little strip where I could barely
Because
draw a
it's
parabola.
like, zoop.
Yep.
And it goes back.
Like what, you know?
So the average speed in that case of d2 minus d1 over t2 minus t1 would be, let's see, 30 minus 0 over 4.1 minus 4. So 30 over 0.1, 300 inches per second. That seem a little closer to maybe what might be realistic? It's more realistic for a punch. But is even this first part of this, from 4 seconds to 4.1, is Ramsey really all that worried about what was going on even at 4 seconds?
No.
Now, it's really right at 4.1 seconds where he's concerned about. That's what he finds most interesting, the point of contact. But here's the problem with instantaneous speed. First problem. If we look at an instant, let's say we look at the instant of contact here at 30 inches, or thereabouts. The speed at that instant would be 30 minus 30 over 4.1 minus 4.1. And what fraction does that give us? 0 over 0. Is that possible?
No.
No. So we must find a way around 0 over 0. Limits are what we've been using.
Figure it out.
We'll figure it out with limits tomorrow. I'm going to do a little bit of numerical today, though.
Oh, way to leave us on a cliffhanger.
I know, it's horrible.
We
you'll
found the evil 0 over 0. Dun, 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 dun.
So some guys are saying, when do you have to worry about 0 over 0 in real life? Anytime you want to know what happens in an instant, 0 over 0 shows up as a problem. How fast did the car hit the tree? How fast are you running right at that split second of time? How fast do you get hit by something?
If a tree falls in a forest, can anybody hear it?
Can you ever find the instantaneous speed with which it hits the ground?
Wait, why would it be 30 minus 30 and then 4.1 minus 4.1?
Well, because in an instant of time, in the smallest amount of time you can imagine.
But it's still like a tiny difference.
Let's see how tiny. Let's find out.
I've helped
Okay,
you in there.
now,
That's pretty good, right?
looking at this graph, okay, here's what we're going to do. I'm going to draw an extended graph. Actually, do you mind if I erase this one?
No.
Okay, so I could use this whole board to be a little better. I'm going to only graph the interesting part of the piecewise function.
Which is everything.
Well, so I'm going to review some basic graphing. I'm not really interested in the first and second part. Okay, guys, if you're going to graph only part of something, you start here at 0. Does anyone remember this from middle school? You put a broken graph in.
Yeah.
And that lets
That's
me,
so cute.
it is, that lets me skip to 4. And now my scale is going to be that 4.1 is way out here. Now normally you can't change scale in the middle of a graph. But if you put this break in, you're basically saying...
Then it's all right.
Yeah, I have no interest in anything that happened before 4 seconds. Between 0 and 4, I don't care. So now I go 30 inches out to 4.1. And now I'm very interested in this parabola, this horribly drawn parabola. Would actually be one of my better circles.
Wait, that's a parabola?
Pardon?
That doesn't look like a parabola.
Well, mathematically we know it's a parabola from my equation over there, so you'll have to forgive my drawing.
We'll forgive
You
it.
dotted the origin.
You hate it when I do that. I know. Okay, when we found the average speed, the 300 inches per second.
Shouldn't it be more of a bell curve?
I don't know.
Because you have to slow down your punch. It doesn't just end.
Oh, it's
Yeah, we're really. This is a very poor approximation, but it'll work.
You show it speeding up and then you don't show it slowing down.
Correct. I'm magic. I'm an 8-bit video game character.
Yeah, I was just gonna say Mario.
I'm Mario. I can change direction without slowing down and stopping in between. Okay.
8-bit.
This isn't a perfect approximation of a punch, but it is a fairly easy one to calculate a derivative for. So, and that's more important today.
Ooh.
What we just found here is the slope of this line is 300 inches per 1 second. So that's what we found. But that's still too big an average. I didn't hit them until way out here. But I can't just do an instant because I get 0 over 0. What I can do is find the slope of the line over a smaller interval. So I'm going to go out here to 4.09. And I'm going to find this slope.
Wouldn't that be 3? No, just joking.
I'm going to find this slope. Now for this, somebody with a calculator is going to have to tell me this y value.
Never.
Never. So either the fastest thing to do might be to put this parabola into your calculator, and you can help me by tracing to various
That's
points as we
supposed to be
go.
a straight line, the red one.
Yeah, it's supposed to be a straight line.
Well, we're trying to find the slope of
Are you
that.
supposed to be teaching us math, Mr. Melville? Because really it's not happening.
But we don't know, is that 15 inches?
Which one?
The red dot?
Oh, this? No. Yeah, I need someone to tell me this y value. I have a vague memory from when I've done this lecture before, and I'm sure my scale is not off. But I need someone to plug to find what f of... Thank you. That's my calendar.
I got a very high line.
Meeting with the...
Okay, so get a... on that.
It's got a line.
May I see? Oh, you got to plug in as x.
Where is it at?
Oh yeah, because that just gives you y equals...
Y equals the answer.
Yeah.
Yeah. So...
A very large answer.
now here, I'll here you go. Ramsey, I'm gonna fix your window for you, and then you will be in a good position to help this, okay?
I don't. You can do it.
No. Really, I wouldn't wanna. There you go. There's that parabola from 4.1 to 4. Okay? Alright guys, now, focus here, okay? Ramsey, trace for me, 4.09, what do you get?
Gee.
4.07, 4.08, 4.0.
Just trace, hit trace and put 4.0.
I know, it's taking forever.
Really?
Yeah, okay, here we go, guys. 4.09, y equals 24.5.
24.5?
Yeah.
Okay, so now, here's what we do. Okay, this is working. So now we're going to find the slope of this line, which will be the average speed over a smaller interval. So now d2 minus d1 is 30 inches minus 24.5 inches over 4.1 seconds minus 4.09 seconds.
Is this us manipulating that?
Yes. So now what we're going to do is, we're doing it numerically though, we're not doing it by algebra. That comes a little later. So now this is 5.5 over 0.001 or 01?
It's negative.
Over 0.01. It shouldn't be negative.
No. Oh, yeah, sorry.
Okay.
I'm so stupid.
No, you're not. And this is 550 inches per second. Is that right?
Shut up.
Double check me on this, guys.
Why are we showing at 4.1?
4.1 is where we're ending at, actually.
Oh, right.
I'm using D2 and D2 and T2.
Could you have chosen 3.12? Like,
You can choose anything you want to, but I'm trying to get closer to that moment of contact. Trying to get closer and closer to that moment of contact. So at first, okay, if you average the whole 30-second interval, think about the progression here. Got to get it all in your head. If you think about the whole 30-second interval, it's 5 inches per second. I definitely hit them faster than that. If you think about the whole parabola and take the average, it's 300 inches per second. Closer. If I just look at the average speed in the last tiny interval, it's 550.
Now you have to look at how many seconds your hand was actually touching my face.
Well, that's a little bit, we're not going to get into that much detail. But now let's go to, let's go out further.
No.
What happens at 4.099?
Oh my god.
What's f of 4.099? We're chasing an instant. I want the slope from here
Is that
to here.
3,000? Yeah.
Yeah. So 3,000 times 4.099 minus 4 squared. What's that equal?
29.4.
Okay, 29.4. Does it go out any more than that, or is that it?
03.
03. It's going to become important. I'm not going to worry about significant digits here. Okay, but I'll tell you something about that in a sec. Now d2 minus d1 is 30 minus 29.403 over 4.1 minus 4.099. What's that slope going to give me? 0.597 over 0.001, right?
Uh, 597.
Yep. So that's 597 inches per second. Keep getting faster.
But
How
at
do you
slower
know when to
rates.
Stop?
Pardon?
Because he accelerates.
How do you know when to stop going to smaller intervals?
Never.
There's a couple answers to that. It depends on the problem.
When your speed gets slower?
When you're pretty sure you're not going to pass something. Mathematically, you keep checking intervals until you're sure you're not going to pass the point. We'll do one more, and then I think you'll know.
Is it when your speed starts decelerating?
Well, what actually happens is mathematically you stop getting changes in the first 5 or 6 significant digits of your answer. When you have to go out like 6 or 7 significant digits to see something change, you're done.
That means we get to rid of a lot of sick things.
Pardon?
So you always have to do at least 5.
Well, it depends on what you're doing. Actually, for instance, if all we cared about was 3 significant digits or 2 significant digits of accuracy, to go back to physics terminology, then we'd actually be done now. We would keep getting the same answer over and over again, and we'd get a different answer than this. But let's do one more.
Actually, wouldn't you go one more anyway? What if it? No, 2 significant digits if it's up to 5.
Yeah, then you wouldn't care. But check this out. 4.0999. What do you get? What is 3,000 times 4.09999 minus 4 squared?
29.94003.
29.94003?
Yep.
Excellent. Okay, so thank you, Nick. So that's D2 minus D1 is now 30 minus 29.94003 over 4 minus 4.0999.
4.1.
4.1.
4.1, thank you very much. And what do we get?
Why didn't we begin? at not using
599.7.
599.7 inches per second. If we had begun with this, we wouldn't be sure of the trend. What do you think this is getting closer to?
600.
600. And actually, what do you, if we'd only done 2 significant digits, Johannes, this would have rounded to 600, right?
Mhm.
And this would have rounded to 600, and this would have rounded to 600. So we're going to call it, we're going to say that it hit at approximately 600 inches per second.
It shouldn't ever get there, should it? Or
Hold that thought. I'm gonna, you
If
know what, I have
get to
time.
the
Are we
instant
not here?
before
Well,
this,
any questions about this? Real quick, before I go on. Do you guys get what we did? We kept finding these shorter and shorter slopes.
Yeah.
yeah, but it shouldn't ever get there, should it?
This is the magic of limits, and this is going to bother Ramsey for the rest of the year. Okay, come back over here. May I erase these calculations?
Yep.
I have just enough time to do this. This is going to be very quick, and this is why there's no homework on this. This is going to leave you with questions.
You suck.
But we'll continue tomorrow, picking up. There's
Does
no...
Harry Potter really die?
Anyway, okay, here's what we were doing. We were finding a slope. One way to think of a change on this axis is to call it delta x, right? Is that okay? All right. Now let's say we were finding the slope from here to the end. In that case, I'm going to shrink my delta x. I apologize, I shouldn't have drawn it there yet. Let's just call this part here a change in x. Is everyone comfortable with that idea? From here to here, x has changed. I'm going to call it delta x. Okay, and then over here on this axis, I'm going to call this point here f of x, corresponding to this x point. If I take this x value, and to this x value I add delta x, okay, I'm going to get to here, to the end of my interval. X plus delta x gets me here. Does that make sense? Okay. Then if this is f of x, this point up here, the y, corresponding to the x where I started,
F of delta x.
no, it'd be f of x plus delta x. Close, Catherine. I like you were thinking about that. It's f of x plus this interval. Okay? Does that make sense? Comfortable with these notations? This is 1x. This is one y value. This is a further y value. They correspond to x and x plus delta x. That means I can say,
Wait, that means you can find the answer.
well, that means I can say the slope is f of x plus delta x minus f of x over delta x, right? Is that a way to write slope? Is that a y minus a y over an x minus an x? And will those y's and x's line up? What we were actually doing was by finding smaller and smaller average velocities, is we were finding the limit as delta x got very, very small of f of x plus delta x minus f of x, y2 minus y1, over delta x, x2 minus x1. We were finding the limit for this. We were shrinking the distance between these time intervals.
Wait, we've been doing this the whole time and we couldn't have just figured it out from one stupid formula?
Well, it's not just one stupid formula, there's a whole family of formulas that comes from this. And you always have to go back to this. This is called the limit definition
The formal definition.
of the derivative. And derivative is an instantaneous rate. The word derivative is used two ways. The word derivative is used to describe an instantaneous rate at a moment of time or a moment on a graph. It's also used to describe a formula that gets you these instantaneous rates. Yes?
Is that on your shirt?
Oh, that shirt I wore. No,
Is that
this
on
one
your
is
shirt?
not. This formula is not on my shirt. The results of this formula are... That shirt actually is a table of antiderivatives. If you know the instantaneous rate, how do you go back to the general function?
Oh my god, you could do that?
Yeah, that's doing it backwards. So that shirt is actually a list of shortcuts on how to do this backwards. But that's what some kids struggle with the most in the second half of calculus, which is on, yes, the AP exam. But for now, let's take a quick look at this. Ramsey was saying, can you reach there exactly? Just enough time to do this. Okay, for the moment of the punch, f of x equaled 3,000 times x minus 4 squared, right? This is going to be very fast, don't worry if you have trouble following it. F of x plus delta x then is 3,000 x plus delta x minus 4 squared, right? I just take x plus delta x, put it in everywhere there was an x in the original function.
Yeah.
So here's what we have to do. We have to find the limit. You know what they do that's fancy? Just to make your lives easier, and I'm going to start doing it now, I meant to wait till tomorrow. They take delta x and they switch it with h. Do you know what the complicated math thinking on that is?
Height.
H's are much easier to draw.
Really?
Yeah, doing delta x over and over
Why
again
don't they
is a
make it
pain
an
in the
L?
ass.
That's the easiest letter to draw.
I know, but it's easy to mix up with other things too. Honestly, I have no idea why they picked H, except it's like one of the easiest letters to do. So,
But then that makes it, because H is also X.
yeah.
We know H is Y.
Okay, so this is going to be f of x plus delta x then is 3,000
Oh really? It's a y upside down.
x plus h minus 4 squared minus x minus 4 squared
4 squared.
all over h. Okay? I have to expand this somewhat quickly. Limit as h approaches 0. I'm going to take the 3,000 out of everything. Is that okay? Okay. Two trinomials. X plus h minus 4 times x plus h minus 4. I am going to get x squared plus xh minus 4x. Distribute the x first. Then I'm going to get xh, h times x, plus h squared minus 4h. Lastly, I'm going to get minus 4x minus 4h plus 16. Okay, so when I notice I wrote them all in the columns. So when I combine them all, I get x squared.
Plus
Plus
2h.
h squared.
Yeah, plus 2xh, good. Minus 8x plus h squared
Minus 8h
plus 16. And that's all over h, which looks like an n. Oh, whoops, what did I leave out? The minus f of x, that's important.
What?
Remember, it's not just
Oh, right.
x plus h minus 4 squared, then it's minus x squared minus 8x plus 16 all over h. A couple things are going to happen here. I've got just enough time to do this algebra. What's x squared minus x squared?
Nothing.
Nothing.
Bye-bye. What is minus 8x minus negative 8x?
Nothing.
Bye-bye.
Bye-bye.
What is 16 minus 16?
Hey, this is
12.
like the rotated.
Oh, it is a little bit like the rotated comics, yeah. It has a similar way to double check, too. If everything without an h in it doesn't disappear, you've made an algebra mistake somewhere. Everything that doesn't have an h should disappear, and all you should have left
The limit does not exist.
is 3,000 times 2xh,
plus h squared minus 8h.
right? All over
8h.
Okay, we can't let the dog off the leash yet. We'll still get 0 over 0. This is actually working. We said that at an instant of time, the average speed should be 0 over 0. So far, that is unfortunately staying true. What I forgot to remind you guys of, if I let h equals 0 anywhere in here, I'd get 0 over 0. But now, after we've done the algebraic manipulations, similar to what we've been doing all week, I can factor an h out of every term on the top, and I'm left with h times 2x
Oh,
plus
over
h
h, so you
minus
can cross
8,
them out.
boom, boom,
Times 3,000.
times 3,000. I'll write that at the end, but thank you for reminding me. So now what I have is equals the limit as h approaches 0 of 3,000 times 2x plus h minus 8. I let the dog off the leash. I allow h to get as close to 0 as it wants. And that h goes away, and my answer is 3,000. I'm no longer writing the limit sign because I performed the operation of allowing h to get as close to 0 as it wants, times 2x minus 8. What this is a formula for figuring the slope at any one point, not between 2 points, but now at any one point along that parabola.
So
It
now
won't help me with any other parabola on God's green earth. It will only help me with this parabola.
So now we plug in a y or an f.
Plug in an x at time. Ramsey, what did I say was the most interesting instant of time on the punch for you?
The hit.
The hit, which we said was at about 4.1 seconds.
For him.
Okay? So,
Most interesting
probably also
is
for
the
my
hit.
knuckle too. I put in 4.1, I get 3,000 times 2 times 4.1
8.2.
minus 8. I'm going to get
It
At
does reach it.
8.2, and this is exactly 600
Yay!
inches per second.
He
You
got
didn't rewrite
me.
limit.
I didn't have to because I performed the operation. After this step, h has reached 0. I actually have started to care about whether it gets there or not. If I let h reach 0 in the first step, it's 0 over 0. If I algebraically manipulate it until the h's all go away except for this one here, and who cares about that one, then I'm left with just 2x minus 8.
It's not going away too much. It's a difference.
Yeah, there's a difference, it's true. This formula, 3,000 times 2x minus 8, that would tell me the slope of the tangent line and tangent line barely touching. That would tell me the slope of a line that barely touches this parabola anywhere along it where I choose to pull in an x. So I don't have to keep doing all of these little calculations over and over again and keep getting closer and closer and guessing.
You just have to do that big one.
You just have to do this big one, but then you get a formula that works everywhere on that parabola. Which is easier? I don't know. What are you being asked to do? This definition, I will not lie to you. There are shortcuts around this. You don't actually have to do this every time when you get to calculus. Am I going to make you do it? Yes, I'll make you do one of these on the final. Make you do one of these. But you don't actually have to do it. You learn shortcuts. However, you learn a shortcut for polynomials. It doesn't work for sine and cosine and tangent. You learn shortcuts for sine, cosine, and tangent to find derivatives, instantaneous rates. They don't work on logarithms. You learn a shortcut for logarithms. It doesn't work on exponentials. Every time you get to a new type of math, a new family of math, a new part, you always have to go back to this. Well, okay, you don't. Someone can just hand you the shortcut. But if you want to understand it, you have to go back to this and re-figure out what the derivative means for that family of functions.
Is this on the AP Calc exam?
And they always throw in a limit definition of the derivative problem on the AP Calc exam. There's one particular type that guys, I could show you. You guys knowing this, I could show you that's really annoying.
Are we gonna spend more days going over this?
Tomorrow definitely, Monday definitely, test
Okay.
Tuesday.
'Cause
Yeah,
this was a lot too.
this was a lot
Do
to
we
take
have to
in.
actually do this
That's why
on a test, really?
Yeah. Now, the other part is, the other thing I want to say about this. When does going back to the limit definition end, and can you just use shortcuts?
Never.
Never. I didn't even know this. I literally got a text just about 2 months ago from a former student of mine, engineer, I mentioned this a few days ago.
Who proved that you
Well-
have to do it always.
Well, yeah, the text said, he said, I'm now an engineer, I'm doing heat transfer models. Anytime something hot touches something cold or other, you talk about the math of how much heat goes back and forth. He says he has to go back to the limit definition of the derivative all the time in trying to figure out mathematical models for how the heat goes from hot to cold or cold to hot. Well, it always goes from hot to cold. So you're never completely done with this. Those of you going on to AP Calculus, you'll be able to ignore it probably 80% of next year because you'll be busy manipulating the shortcuts. But it'll be on the exam, and you never stop going back to it. This is what a derivative is. This is what an instantaneous rate is right here. Don't confuse the shortcuts with this. Okay?
I used to like
Thank you.